In this video, we will explore a representative dimension reduction technique called principal component analysis, PCA. For your information, 2 separate videos are available. In this video, we will take a look at the theoretical part of PCA, and then the coding aspect in the other video. Principal component analysis, PCA, is the most widely used dimension reduction technique in artificial intelligence and statistical analysis. As mentioned in the previous dimension reduction video, PCA is an unsupervised method, meaning it learns from the X data alone without Y data. Through PCA, we can extract important features from multiple characteristics, visualize data, and simplify the analysis process by reducing dimensions. As shown in this slide, when we have a dataset with n observations and p features, nxp, PCA can reduce the number of features to a smaller value, k, where k is less than p. For example, if we have data with 10 features, we can reduce it to 2 features using PCA. It's important to note that PCA doesn't simply select existing features as they are, but rather performs a linear transformation to reduce the dimensionality to new features called Z1 and Z2. This makes PCA fall under the category of feature extraction. When the number of features is 10, visualizing the data in graph form can be difficult. However, if we can reduce it to just 2 features, like Z1 and Z2, it becomes much easier to visualize the data in a 2-dimensional graph. This is one of the crucial reasons for performing dimensionality reduction. In this case, the newly created axes, Z1 and Z2, to which the original features are transformed, are called principal components. So we can think of projecting the data points that originally existed in the 10-dimensional space onto the newly created 2-dimensional axes Z1 and Z2. That is, the data points are mapped perpendicular to the z-axes, just as we discussed in the previous eigenvectors and eigenvalues video. The question then arises, how do we find these new axes or principal components, Z1 and Z2? Let's explore how to obtain these principal components in the next slide. To further aid understanding, let's consider dimensionality reduction from 2D data to 1D. In PCA, we aim to find a new axis that represents the data distribution best from the center of the data. Therefore, we are interested in the variance of the data. So, the data points are mean-centered, and then moved vertically onto a single straight line. Now, among the 3 axes shown here, Z1, Z2, and Z3, which one should we choose for projection to be the most appropriate? When we move 2D data onto a single line, the data distribution becomes narrower, indicating that some of the data points may overlap, making it difficult to distinguish them. So, finding the best axis means finding the axis where the projected data points are most spread out and do not overlap as much as possible. A wide distribution means a large variance in the data. Therefore, what we ultimately need to do is to find the axis with the largest variance. Now, let's explore how to find the axis with the largest variance in the data. Before that, let's take a look at the covariance matrix, which represents the covariances between different variables. Variance measures the extent to which data is spread out. If the data is widely distributed, the variance is large, and if it is tightly packed, the variance is small. Covariance is an extension of variance for multiple variables. For 2 variables, let's say x and y, the covariance helps us understand their linear relationship. If the covariance is greater than 0, it indicates a positive correlation between the 2 variables, and if it's less than 0, it indicates a negative correlation. On the other hand, if the covariance is 0, it means there is no linear relationship between the 2 variables. The covariance matrix is a square matrix with the same number of rows and columns, and it contains the covariances between different pairs of variables. Let's take a closer look at the covariance matrix for the variables z1, z2, and z3. Elements in the covariance matrix represent the covariances between pairs of variables, so the diagonal elements represent the variances of each individual variable. For example, the covariance between z1 and z1 is simply the variance of z1. The same applies for z2 and z3. On the other hand, the off-diagonal elements represent the covariances between different pairs of variables. For instance, the covariance between z1 and z2 shows how these two variables are related. In PCA, we seek to find the axis with the largest variance. This means, from the covariance matrix, we are looking for the z values along the diagonal that have the greatest variance. In other words, we are interested in the z values with the highest variance, which are crucial for the dimensionality reduction process. When we multiply a vector by a matrix, the vector undergoes a linear transformation. Similarly, when we multiply a vector by the covariance matrix, it undergoes a linear transformation, resulting in the creation of new vectors. Among these newly generated vectors, the arrow-marked vector represents a special case where the direction remains the same both before and after the multiplication by the covariance matrix, while only the magnitude changes. To help you understand, let me explain using a simple example. Here on this graph, we have green dots, and when we multiply a 2x2 covariance matrix by these points, they transform into this elongated shape. Among these transformations, let's focus on the vector represented by the arrow with 2 and 1. When we multiply this vector by the covariance matrix, we can observe that it becomes equivalent to multiplying it by the number 11. In other words, the result of multiplying the covariance matrix A is the same as multiplying it by the scalar value lambda, which is 11 in this case. A vector has both magnitude and direction, and when we multiply a vector by a scalar, its direction remains unchanged, while only the magnitude or scale changes. For example, if we multiply a vector with components 1 and 1 by 3, we get a new vector with components 3 and 3, maintaining the same direction but with a different magnitude. Now, when we multiply a vector x by a matrix A, and the result is proportional to the original vector, it means that the matrix transformation only changes the magnitude of the vector, and the direction remains the same. In this case, we call x the eigenvector, and the proportional value, lambda, the eigenvalue. In summary, eigenvectors represent the direction, while eigenvalues represent the scaling factor of the transformation. Thus, larger eigenvalues indicate that the vector's magnitude increases, which means that the data distribution spreads out, resulting in larger variance. By the way, there is a video explaining eigenvectors and eigenvalues, which will be very helpful to understand this topic. Now, returning to the covariance matrix and summarizing what we've discussed, when we multiply the covariance matrix A by the eigenvector x, it is equivalent to multiplying the eigenvector by the eigenvalue lambda. In other words, the covariance matrix, A acting on the eigenvector x, results in the same outcome as the eigenvector scaled by the eigenvalue lambda. In practical terms, this means that the variances of the principal components, such as z1, z2, z3, which lie on the diagonal of the covariance matrix, can be expressed as the respective eigenvalues lambda 1, lambda 2, lambda 3. So each principal component's variance is associated with its corresponding eigenvalue. In the previous slide, we discussed how in PCA, we aim to find the axis that results in the broadest distribution of projected data points, where they do not overlap with each other. In other words, we want to find the axis with the largest variance in the data. As the eigenvalues increase, the length of the corresponding eigenvectors also increases. This means that the data distribution becomes broader, resulting in larger variance. Therefore, to find the principal components Z1, Z2, Z3, and so on, we simply need to identify the ones with the largest eigenvalues. These principal components will capture the most significant variability in the data. In summary, principal component analysis selects the principal components as the axes for dimensionality reduction, based on the axis that exhibits the largest variance in the data. This large variance is represented by the eigenvalues, and the eigenvectors associated with the largest eigenvalues are selected as the principal components. As shown in this illustration, Z1, which corresponds to the largest eigenvalue, becomes the principal component, suggesting that 2 dimensions are reduced to 1 dimension. In the next video, we will explore what kind of results we can obtain from PCA and learn how to implement PCA in coding.